We're going to start by creating the schematic for this project, the 555 timer-based servo controller. I already have KiCad open. Find the top left button, create a blank project. Click that and give your project a name. I'm going to call it servo controller 555. There's a bit going on in this circuit. There's a signal generator for driving the servo, and there's also a power regulation side of things, which is a really useful tool to keep in your back pocket for your future circuits. Open up the schematic editor for the project, and let's start by placing our first component, the 555 timer. You can find the place component symbol over on the right, or you can strike the A key to open up the KiCad libraries. Now the KiCad libraries, there's a lot going on here. You can see there's huge amounts of parts, but it's very, very searchable. Each of these is just a different family of devices, so you can explore this in your own time. But to get started, we can just type in 555, which gets us a bit of the way. I know that we want to be in this timer library, but we can just include more keywords. 555 timer, and it's expanded us into the timer library, and it's even selected a part already. You can see it's selected this row. This is what the schematic symbol looks like, and this is what the physical footprint that is going to look like on the circuit board. We can see that this is a surface mount part, which is not what I want for this part of the circuit. So I'm going to search for something that's through hole or dip. And now we have the LM555N, which is a PDIP8. That means it's a dual inline, and we have 8 pins that go through the board. This is a through hole part, and it has the same symbol. So I'll double click that, and we'll place that right in the middle of our schematic. Now, before I place any more parts, I'm going to connect this one to power and ground. And on symbols, these are usually at the top and the bottom of the symbol. We can see at the bottom, pin 1 is ground, and in the top, VCC is the convention for positive voltage. Come over to the power symbol, or strike P to open up the power symbols menu, and I'll look for, I know that we're going to be using 5 volts, so I'll just type in 5 volts to be completely unambiguous about what VCC is. VCC could be anything within a range that this device accepts, but I know that we're going to use 5 volts. Strike P again, and we'll place the ground symbol. You can type GND to search for ground and place that down here. It's nice placing these first because it keeps our schematic clean of lines that would otherwise be crossing all over. These don't connect to anything yet, but we'll get there later. I can see we're going to need a capacitor on pin 2, so I'll strike A to access the components, and just search for the letter C. C is the generic unpolarized capacitor symbol. There is also a polarized capacitor symbol as well that you can use for like electrolytic capacitors, but I know that we're going to be using a ceramic capacitor, so I'll just select C and place that near enough to pin 2. Now to connect it, I want to hit Escape to deselect my current tool, and now I can just click on the connection for the capacitor and drag that wire over to pin 2. So the wire tool is automatically used when we click on one of these unpopulated pins. I could draw a wire all the way down to ground for the other side, but I'll keep my schematic clean by copying that and just pasting it there. Of course, all components have values, and this is a 22 nanofarad capacitor. So I can hover over the capacitor and strike V to go straight to the edit field for the value. I can put in 22N or 22NF as you like. You can edit other properties by striking E to access the full symbol properties menu. And if you get lost or confused, you can always just right click and find that properties menu. But V is a great shortcut. Similar to searching C for capacitors, we can search for R to place a generic resistor symbol. These generic symbols, remember, they don't have any footprint associated with them, but at the moment we don't really care. We just want to capture the design intent of the schematic onto the page, and we can worry about the physical realities of things later. So I'll place that resistor. I'm also going to need a diode, so I can type D for diode and just put in a generic diode symbol. I'm going to need a potentiometer, so I can start typing pot. And here we have R potentiometer, and it's a 3-pin device, which is exactly what I want. There are dual gang potentiometers that are optional as well, but I just want this 3-pin device. Now that's it for all the unique components that we need for this controller circuitry. We know how to place parts and we know how to wire them up and set their value. So I'm going to zip through and complete the schematic, and I'll see you when I'm done. Here my labels are colliding for these components. There's a couple of solutions. I can click and drag those away, or I can select the component and strike X, not X, Y, to flip it vertically to move those labels out of the way. Our signal generator is pretty much complete. I just copied all those parts and connected them as per the reference schematic. I added this decoupling capacitor. It's very common to have 100 nanofarads as close as possible to the VCC and ground pins of integrated circuits. It helps to filter their supply voltage. The only thing that's missing is the output connector. We need a 3-pin header because our servo has a 3-pin connector on it. Strike A and search for CONN. We can open up the connector library, and we have these generic connectors here. You can see CON 1x1, 1x2, 1x3. I want a 1x3 pin connector. So I'll double click that and I'll rotate that around like so. I'm going to connect ground to pin 1, 5 volts to pin 2, and our signal will go to pin 3. And that's the 3 wires of the servo. Black is ground, red is power, and then white is the signal. And we have this wire crossing over our schematic here, and it also means that our connector is kind of tethered spatially to where our circuit is. Maybe we don't want that. Much like how we use these power labels to join 2 parts of the schematic without wires, we can use a net label where a net is just a connection. Everything that's connected together is on the same net. And we can come over to the Add Net Label tool and just label this net as SIG. Or maybe it would be better to use signal. Now we can delete this wire and connect signal to our connector. And we can copy that with Control-C, Control-V, and we can wire it in to the 555 timer. And now our output connector is completely decoupled from this part of the schematic. This is really powerful, and it means that we can separate our schematic into functional chunks that are joined either by wires or these net labels. While I'm here, I'll label this connector as servo. And this is the signal generation side of our schematic done. It's complete. Now we still have the power regulation part of the schematic to build. That's the part that will accept any voltage between, say, 7 and 12 volts and convert it into a nice stable 5 volts. I'm going to zip through it now and see you at the end of that process. You'll be able to follow along or use the names in the reference schematic to find the right parts. A quick recap about what we've just done. We have a screw terminal for our power input. That way we can put bare wires into a screw terminal with 12 volts, or we can just solder them directly to those solder pads. We have a rectifier diode or a reverse polarity protection diode. In case we get this backwards, it's not going to break our circuit. We have an LED and resistor to indicate that we have the presence of 12 volts nominally. A voltage regulator steps 12 volts down to 5 volts, and that's going to be used to power the rest of our circuit. And we also have a power indicator LED and resistor pair there as well. And as best design practice for this regulator, we use a polarized capacitor, and that nominally has a value of 22 microfarads. For the voltages we're talking about, it's pretty safe to use a 1K resistor for these resistances. This diode is just going to be any jelly bean rectifier diode that we can find. And that is it. We've completed functionally our schematic design. There's still a few nice things that we could do for quality of life. We could add our name and project name to this title block so we can share our project or keep track of changes. And we can organize the schematic into functional blocks with some helpful comments. So I'll do that right now. You can find this third button, which is the settings for the title block. I'm going to call this the Servo Controller 555 for new teams. And I'll just put my name as comment 1. We can click OK and we can see that information is now populated into the title block. There are some graphical elements that we can include on the schematic to help organize it. I'll drag this functional block to the side and just add some text. Servo signal generator. And I'll make this quite large, 2 millimeters and bold. Now we have this nice title. And we can do the same thing over here. I'll just copy that to use the same settings. Power input and regulation. So now we've got these nice labeled circuit blocks. And if we, as this circuit gets more crowded, it may be even useful to just draw a box around each group. You see that quite a lot. So we can just draw that. And this is our servo output. To enter that element quickly, I just double clicked it and it seemed to understand what I wanted to do. And so there you have it. This is a non-trivial first schematic. There's quite a lot going on here, but as you can hopefully see, it's just repetition of the same tools and ideas. We've put down a lot of unique components. I would say that this is probably a pretty high level first schematic. It has 2 active components. It's got the power regulation side of things. It has the pulse generation side of things. But if you're referring to that reference schematic, you really just have to make it look the same. And it always helps to make your schematic look beautiful with these functional blocks because then it's easier for other people to follow in the future. Now the schematic just captures the intention of the design, how things connect together. It has no real bearing on the physical reality, how big parts are, how big their footprints are. We saw that this 555 timer comes in multiple different footprints and we just chose one. For these other components, for these diodes, the potentiometers, capacitors, LEDs, it's up to us now to choose the physical footprint that these are going to be attached to because LEDs come in lots of different shapes and sizes, potentiometers, diodes. We've used generic symbols, but now it's time to couple those generic symbols with the physical reality that's going to go onto your circuit boards. Join me in the next video where we'll assign some footprints.